Hey guys, all right, welcome to our last unit, Unit 5. Let's start with Introduction to Unit 5, the need for exponential models. Let's compare a few different table/growth trends. Table number 1, you have an input and output table, aka X and Y table. As you can see, the change in the X is a difference of 1, okay? So that means I'm adding 1 from one number to the next to get your subsequent term. Now on the Y, as you can see, I can add 2 to each to get the next Y value. Now the X has the same increment, okay, so the X, same increment. Y also has the same increment of 2, so same increment. So because the Y is the change in addition, it's a linear, and that 2 value, all of these right here, that's your slope. So that right there is going to be your slope of 2. Now, if I were to ask you to write a linear equation for that, we can write it as a y equals mx plus b, or we can use the points-of form equal to m times x minus x1. So now we definitely can write the slope right away. The slope is going to be 2. But we need a y-intercept. Now, y-intercept is when x is 0. We can go backwards. If we know the increment in x is 1, so the one before that would be 0. We know the increment in y is 2, so the number before that would be 2. Because if we subtract 2, going backwards means you subtract 2 to get the y value. So with that said, the slope is 2 from the y increment. X is the variable, b is your y-intercept, so that is going to be 2. So this linear equation happens to be 2. Now let's do the same thing for the next table to see if it's linear or we are now starting an exponential model, and I will explain that. First, check out the X. X has an increment of 1. Awesome, right? Then the Y, we go from here to here, we add 3. From here to here, we add 5. From here to here, we're going to add 7. That is not the same increment, so we can say this is not linear. So right now, we will say that that's not linear. I will define exponential in just a little bit. Now let's go to the next one. X has an increment of 1. Perfect. We always want it to be the same increment if we are to identify as a linear. Now on Y, this is plus 7. This is an addition of, let's see, 27, take away 8. Ooh, that's definitely not 7. So that's going to be what? 19? Okay, so plus 19. Then this one, 27 and 64, that's a difference of 37. Ooh, okay. So you can see the increment in Y for letter C is not the same. So again, we're going to say it's not linear. Okay. Then let's move on to the last one. D, again, the increment in X, they are all the same. They are 1 unit addition. The increment on Y, let's check that out really quickly. I'm going to add 10 here. This is 20. And from here to here, this is going to be adding 40. Okay, so that's not linear either. Okay, so now how do we decide if it's not linear? How do we decide that's exponential? Now, before we go to exponential, I want to give you a basic model. Normally, the basic model for exponential is your y equals A is a vertical stretch compression if it's negative, a reflection, times B is your base, and then an exponential is now the exponent. That's why it's called the exponential. So to determine whether the function is exponential or not, if it's not linear, then it can be an exponential. So now let's go back and see if the multiplication is the same. So from here to here, I would multiply by 4. Well, from here to here, it's not 4, okay? So not 4. So right here, it's not exponential. So that one is not exponential. So that's neither. Now, from here to here, I would multiply by 8. From here to here, I'm not multiplying by 8. So the ratio is not 8. So that's also not exponential. Let's look at the last one. From here to here, we would multiply by 2. From here to here, I'm also multiplying by 2. And from here to here, I'm also multiplying by 2. So as you can see, the ratio is the same. Well, guess what? If the ratio is the same and the increment in x is identical, then now we can say that it is an exponential function. Yay, that's what. Okay, so now how do we write an exponential? The a is going to be, so let's focus on the base really quickly. Your base will be this guy's right here. So that's going to be 2 to the x. Now the a value is going to be, what do we need to fill in? So that way, when I put 1 in for x, I would get an output of 10. Well, let's test it out really quickly. If x equals 1, so 2 to the 1, that's only 2. Well, what must we multiply in the front? So that way we get a y value of 10. Would you agree that in the front, we would need to multiply by 5? So that's your a value. A value for this case is going to be 5. And that is your exponential. No, you do not multiply 5 and 2. You leave 5 times 2 as the equation. If you write it like this, it would be completely wrong. Y equals 10 to the x. That would be completely wrong. So do not do it that way. So that's how you decide whether it's linear or exponential or not, okay? Because not everything is linear and not everything is exponential. So let's move on to graphing. Graphing is going to be very similar to it. Let's start with our lesson. It's called an exponential. Your parent function is we don't have any a value, you don't have any h value, and you don't have any k value. Now, you can see the a is in the front. This b value is your base. Okay, the h is still a horizontal left and right, and the k is still vertical up and down. So make sure you have a blank space right here. Remember, your parent function will be different depending on your b value. We are going to start with a parent function that has a base of 2. Now, every single parent will be different depending on your base. So if base is y equals 3 to the x, then you're going to have a different value. First thing we want to do is start with the input and output table. We will go -2, -1, 0, 1, and 2. And we're just going to enter it in. So the base is 2. So 2 to the -2, which is going to be 1 over 2 squared, which is going to be 1/4. 2 to the -1, it's a negative exponent, so you move it to the bottom, which is 1 over 2 to the first, which is really just 1/2. Next is going to be 2 to the 0 power, 2 to the 0 power, so that's going to be 1. 2 to the 1 power is going to be, frozen on me, so give me a second. 2 to the 1 power, 2. 2 to the second power is going to be 4. So these are your inputs and outputs. Let's give it a little graph. -2. I'm going to rescale this because it looks like we have very small inputs and outputs. So what we're going to do is I'm going to rescale it. Every 2 boxes is now 1 unit, okay? So that way we have just a little bit bigger graph to see. And then this is going to be 1, 2, 3, 4. -1, -2, -3, and -4. And I'm going to use a different color to plot my dots. -2, we're going to go to a positive 1/4. Oops, that's a -3. So positive 1/4. Try your best to approximate that dot. -1, it's now a half. 0, go up 1. 1, go up 2. And 2, go up 4. So here's your smooth. Make sure this is not, okay, it's a smooth curve. And it can go up forever and to the left forever. So as you can see, doesn't matter what I plug in for x. Let's see what happened if I plug in 1,000 or -1,000. Is the y ever going to be 0? So let's check it out. 2 to the -1,000, which is really 1 over 2 to a +1,000. Well, 2 to the +1,000 is a very, very small number. Let me just see if I can get you that answer really quickly. So 2 to 1,000 is a small, 2 to 1,000 is a big number, I'm sorry. But 1 divided by a big number is small number. It's a very, very tiny number. But it's never ever going to be small, tiny number. Just, it's never going to be 0. So what's happening is you have an asymptote right here. Remember, an asymptote represents what it cannot be, okay? So an asymptote means I cannot ever be 0. In addition to that, I can never be -y either. So the range for the exponential function is going to be y must be bigger than 0 as an interval notation, 0 non-inclusive, all the way to infinity. Now, if you check out the x, which is your domain, it's all real numbers, or you can write from negative to positive infinity. Now, the h and the k value, this is the parent function, so we don't have any translation left, right, or up and down. This is an exponential growth, okay? Growth means as I'm going to the right, y's going up. Now, another way to identify is the base. The base is bigger than 1. Okay, again, the base is bigger than 1. When I say bigger than 1, I'm saying, okay, it can be 1.2, 5, 7. And then we'll talk about decay in a little bit. When would that be a decay? So this is going to be a growth. X-intercept for the parent function, we do not have any, so we're going to say NA. Y-intercept is when x equals to 0, so based on our table, it's 0, 1. It is definitely an increasing interval because it's a growth, so -infinity to infinity. That means nothing is left for decreasing interval. The rate of change varies, and let's talk about the rate of change really quickly. So on this question right here, that's an exponential, and then when we were doing the addition, can you see that the rate of change, it changed from 10 to 20 to 40, so that's why we say it varies. It is definitely 1 to 1, so yes, we don't have any vertical asymptote, but we have a horizontal asymptote, and it is at y equals to 0. Okay, so this is your asymptote, y equals to 0. So for now, let's fill out your blank space on your notes packet. This is a refresher of all the transformation. You can pause it and finish writing if you need to, but I'm going to move on. Okay, again, if you need to pause so you can write it. Okay, steps to graph any function in HK form. Number 1, identify the parent function. Probably check for the base, okay? Make a table value for the parent, identify your AH and K, list the transformation from the parent, make a table of the transformation value by multiplying the A value, add or subtract the HK value, and then plot your new points. So this is another parent function. See this right here? Well, this parent function has a base of 1/2. So let's see the difference, x, y. We're going to do the same 5 inputs. Okay, so here we go. 1/2 to the -2, which is the same thing as 1/1/2 to the power of 2. Let me erase this because I need a bit more space. Okay, so that means it's a little frozen, so give me 1 second to unfreeze it. Okay, so that means it's 1, nope, still frozen on me. It's 1 divided by 1/4. I don't think it likes being this stretch out. So let me just unstretch it out. Okay, so 1/1/4. Well, 1 divided by 1/4 is the same thing as saying it's 1 times 4/1, which is going to be 4. Okay, so, but that's, okay, so as you can see, I use a lot of steps just to get there. Now, just to remind you, let me move up here because I don't want to use up the entire table to show the work. As I'm going up here, so from now on, if you have a fraction, and again, I'm waiting for it to unfreeze. If you have a fraction and you're being raised to a negative exponent, okay, you can flip the inside first and change the negative exponent to the positive exponent. Oh my gosh, Shy, it's like totally frozen on me. Okay, so the -2 exponent, you can rewrite it as a positive 2 exponent, and you will get the same exact answer as 4. So again, to make things quicker, when you have a fraction and it's being raised to a negative exponent, you can flip the inside fractions. So next is going to be -1 for x, and I'm going to use the same 5 inputs, okay? So -1 power is next. Again, we're going to flip the inside fraction, raise it to the power of 1. So that means it's going to give you 2. 0, 1/2 to 0 power is always 1. 1 to 1 power. So 1/2 to the 1 power is now 1. And I'm out of space. So we are going to move it, how about over here? Make an extra x and y, okay? Next is 2, so 1/2 to the 2nd power, that's going to be 1/4. You should have 5 inputs all the time. So I'm going to, again, looks like I have very small x and y, so I'm going to rescale my x axis here. Okay, so let's plot. At -2, we have a y value of 4. So -2, go up 4. -1, we are going to go to 2. 0, go up 1. And then, oh, can you fix this for me right here? See, I wrote 1, but it should be 1/2, okay? So that should be 1/2. So at x equals to 1, y is 1/2. And last one, when x is 2, y is 1/4. Just like when the base was 2, you are going to have an exponential function that will not be touching your x-axis. So what that means is that y can never ever be 0. Now more so, not only that it can't be 0, it can never be negative. So y for exponential, it's always going to be bigger than 0. So your range, oops, why am I writing that in the x, y, and z? The range is y is bigger than 0, or we can write it as an interval notation from 0 to infinity. your domain will always be all real, and we can write it in a notation as well. Now, this is not an increasing, it is a decreasing the entire domain. If it's a decreasing, it's a decay. And decay means your base, okay, your base is actually, actually I'm gonna write it like this, okay? Your base is less than 1, but bigger than 0, okay? So again, your base is less than 1, but bigger than 0. So for example, 9/10, that would be less than 1, bigger than 0. It can be 1/3, 1/7, 4/5, anything like that. That will be your decay. Now everything else is very similar. Your h and k currently would be 0. Your x-intercept when y equals to 0. Right now, it looks like you do not have any x-intercept. Y-intercept for all exponentials, the parents that is, will always be 0, 1. Rate of change will vary, okay? It is a 1-to-1. You do not have a vertical asymptote. You do have a horizontal asymptote because we say that y can never be 0. So horizontal asymptote, y equals to 0. Y equals to 0 is the asymptote. So let me just pinch this in so I can have the entire picture. Next question says, compare the graphs of number 1 and number 2. Now you are to do this on your own. Tell me some things that you see, that the differences between when the base is a half and some differences you see when the base is 2. Some common things or differences, okay? So spell that out right here for me. So that is what you're doing on your own. Go ahead and hit pause, finish that up.